When you hear concurrency and Go, your mind probably jumps straight to one thing: speed, right? Making your code run way faster. But here's the thing that's so cool about it. The exact same tools that give you that raw power can be used to solve completely different problems in some really elegant ways.
I mean, just think about that. What if you could use the exact same feature to both speed up your code and make your memory management way simpler? That's a huge deal. Usually, you're juggling those two things as totally separate problems, right? They're two different headaches. While in Go, they can actually share the same solution. So let's actually break this down. We're going to look at two really powerful patterns that show you exactly how this works. The first one is all about that pure parallel speed we were talking about. And the second one, it's all about some super clever resource management. It's a perfect way to see Go's design philosophy in action. All right, first up, pattern one, the parallel power-up. This is the classic stuff, right? Using concurrency for just raw speed. We're talking about taking a big, heavy job, chopping it up, and running it on all your CPU cores at once to get the answer fast. So picture this. You've got this massive chunk of data, maybe a huge slice or an array, and you have to do some really expensive, time-consuming calculation on every single piece of that data. Now, if you do that one by one, oh man, it's going to be slow. We've got to find a way to do it in parallel. The strategy here is actually super simple, and that's what's so great about it. First, we divide the work. We just chop that big job into smaller pieces. Second, we launch a Go routine for each piece. Think of them as little workers. And third, we just need to wait for them all to tell us they're done. That's it. And here's where the Go magic really kicks in. To launch one of these workers, all you do is type the word Go in front of a function call. That's it. Boom. That function is now off and running on its own concurrently in what's called a Go routine. So we just loop through our data chunks and launch one for each. Okay, so we've got all these workers running independently. How in the world do we know when they're finished? Well, we have to give them a way to call home, right? A way to signal back to us. And in Go, that's what a channel is. It's just a communication pipeline. In this case, we're making a channel that's big enough to hold one "I'm done" signal from each of our workers.
This next part is just so elegant. After we've launched all the workers, our main program just has to wait for those signals to come back. And this little piece of code right here is how we do it. That line will literally pause. It will block until it receives a signal from the channel. So we just loop, waiting for one signal for every worker we launched. Once we've received them all, we know the job is done. Simple as that.
Now, a really important question is, how many workers should we create? You don't want to just hard code a number, right? Well, Go helps you be smart about this. You can ask the runtime how many CPU cores are available with runtime.num CPU. But even better is runtime.geomaxprocs. This actually honors any settings the user has put on their system, so your program plays nicely with everything else that's running. It's a really good practice. Okay, before we get to our second pattern, we need to talk about a really, really important distinction. This idea is basically at the core of Go's entire philosophy. And it's this: concurrency is not the same thing as parallelism. The key difference really boils down to structuring versus executing. See, concurrency is how you structure your program. You design it as a bunch of independent things that can happen. Parallelism is when you actually execute those things at the very same time on different CPUs. Think of it like this. Concurrency is the plan to build a house with a bunch of separate tasks. Parallelism is having multiple workers actually doing those tasks simultaneously. And that leads to this really famous quote: Go is a concurrent language, not a parallel one. What that means is, Go gives you amazing tools, Go routines, channels, to design your program concurrently. Then, if you happen to be running on a machine with multiple cores, the Go runtime is smart enough to take that concurrent design and run it in parallel for you. The focus is on giving you the right tools to structure your thinking. All right, let's switch gears completely for pattern number 2, the clever leaky buffer. Now we're going to take the exact same tools, Go routines and channels, and use them for something that has nothing to do with raw speed. Instead, we're going to build a really slick and efficient system for managing resources. So here's the new scenario. Imagine you're building a server and it's constantly needing these little temporary chunks of memory, these buffers, to handle requests. Now, creating a new one from scratch every single time and then waiting for the garbage collector to clean it up, that's actually pretty wasteful. It puts a lot of unnecessary strain on your system. The obvious solution is to create a pool of buffers we can just reuse, right? But here's the genius part. We're going to use a buffered channel to be that pool. That's right. Instead of sending data through the channel, we're going to put the actual ready-to-use buffers in the channel. It's such a clever way to repurpose the tool.
Okay, so let's think about this from the client's point of view. You're a piece of code, you need a buffer, and you need it now. The last thing you want to do is sit around and wait for one.
So what does the client do? Using what's called a select statement, its first move is to try and grab a buffer from our free list channel. This is the happy path, right? If there's a buffer just sitting there in the pool, we snatch it and we're ready to go. Perfect. But what if the pool is empty? What if there are no buffers in the channel? This is where the magic happens. A select statement can have a default case. And if none of the other cases are ready, meaning if we can't get a buffer from the channel right away, the default case runs instantly. So instead of waiting, our code just says, fine, I'll make a new one myself. It never, ever gets stuck. It's a non-blocking operation, which is awesome for performance.
Okay, now let's flip it around. Let's say a server has finished its work and is done with a buffer. Its job is to try and put it back in the pool so someone else can use it. So again, using a select statement, it tries to send that used buffer back into the free list channel. If there's an empty slot in our pool, great, the buffer goes back in, ready to be picked up by the next client.
But what if the pool is already full? What if our channel can't take any more buffers? Well, this is the leaky part of the pattern, and it's brilliant. The default case kicks in again, and this time, we do nothing. We just drop the buffer on the floor, metaphorically speaking. We just let it go, and Go's garbage collector will eventually come along and clean it up. We never block, we never wait. It's this beautiful, practical decision to say, it's better to lose a buffer occasionally than to ever get stuck. So we've looked at two totally different patterns using the exact same tools. What's the big idea here? What should you really take away from this? It all comes down to just how flexible and powerful Go's concurrency tools really are.
Let's just quickly recap what we've seen. First, concurrency isn't just a hack for speed, it's a powerful way to structure your programs. Second, channels are way more than just pipes for data. They can be resource pools, signals, you name it. Third, that select with the default case, that's your secret weapon for writing code that never gets stuck. And really, the big picture is that Go's features let you solve some really complex problems with code that is surprisingly simple and easy to understand.
And that really leaves us with a final question to chew on. We've seen channels used for speed and for resource management. If you start thinking of them not just as ways to send messages, but as these fundamental building blocks for coordinating work, what other classic tough problems in computer science could you solve with this kind of elegant simplicity?